Okay, this is the M1 paper from October 2023. It's question number 3, and this is a collisions question, but actually there's going to be some conservation of linear momentum as always. There's a little bit of SUVAT in there, and there's even some dynamics as we go through the question. So let's get started and read into it to see what we've got to do. It says we've got a hammer is used to hit a tent peg into soft ground. Hammer has a mass of 1.8, tent peg has a mass of 0.2. They're both modelled as particles, and the impact is modelled as a direct collision. So let's see what's happening beforehand. I've already drawn a quick sketch of what I've got with the two objects. So this is the hammer, and this is going to be the peg. And beforehand then, what we have is that the hammer is moving with 10 meters per second, and as we say, that weighed 1.8 kilograms, and the peg, which weighs 0.2 kilograms, isn't moving at all. So I can put 0 there if you want, just to make it nice and clear with what we're going on. Afterwards, the hammer and the tent peg move together vertically downwards with the same speed v. So that's called coalescing, when basically what we're going to have is the two of them, will be together here, and they're both moving down with a speed of v. This is after. So the 1.8 and the 0.2 will be joined together. It'll be a mass of 2 kilograms now, with a speed of v. So if we're going to try and work out what v is, we say using the conservation of linear momentum, let's write out what that is, which is m1u1 plus m2u2. The initial momentum is equal to m1v1 plus m2v2. Initial momentum is equal to final momentum. And what have we got? So for the first one, we've got 1.8 multiplied by 10 plus 0. The peg isn't moving. That's equal to, and now you could do 1.8 times v plus 0.2 times v, or you can straight away do 2 times v, because 2 is the total mass of the two of them. So that gives us that 18 is equal to 2v, which gives us that v works out to be equal to 9 meters per second. So we know that the joint object is moving at 9 meters per second. Find the magnitude of the impulse exerted on the tent peg by the hammer, stating the units of your answer. Okay, so if I want impulse, part B, impulse is always equal to mv minus u, and we had 0.2 kilograms, and it wasn't moving at all at the start, but it ended up moving with a speed of 9. So that's simply going to be 9 times 0.2, 1.8. I always use Newton seconds for impulse. So I'll stay with my traditional units for that one there. So it's part B done. And then part C, this is a little bit unusual, but certainly doable. It says, the ground exerts a constant vertical resistance force, magnitude R, bringing the hammer and the tent peg to rest. After they've travelled a distance of 12 centimetres, can we find what the value of R is? So yeah, the value of R, I'm going to need to do F equals ma, but I'll need to know what the acceleration is. So in order to work out what the acceleration is, I'm going to do SUVAT first of all. So my object, S, U, V, A, and T. So U is that speed V that thing was moving with, 9 meters per second. The object is going to go down to 0, isn't it? It's going to stop moving. The acceleration is what I'm trying to work out. So that's my A here. Now, this is the thing you've got to be careful with. It's 12 centimeters, so they're just trying to catch us out with our units. 12 centimeters is 0.12 meters, so don't let that catch you out. S, U, V, and A, where A is the thing I'm looking for, not interested in T, where A is the thing I'm looking for, that's going to be v squared equals u squared plus 2as. So when we put this in, 0 squared is going to be equal to 9 squared plus 2 lots of A lots of 0.12. Now, obviously, I'm expecting A to be a negative. It's slowing something down to 0. So when we rearrange all this, A actually works out to be minus 337.5 meters per second squared. And so I always encourage my students just to have a think about it. Yeah, it's come to rest really, really quickly, hasn't it? In 0.12 meters. So the acceleration must be pretty extreme, or rather the deceleration, the negative acceleration should be quite a big number there. So that's not causing me any concern. And then I'm trying to work out what the forces are. So let's draw a quick diagram of what we've got going on. So we've got this object, I don't remember how I draw it, but what's happening is there is a resistive force acting there, and obviously we've got mg acting down here. Now actually mg we can change to 2g, and we know we're trying to work out what the acceleration is there. It's going to be a negative acceleration, but what the acceleration is there. So if I take that diagram now and just resolve vertically, we're going to get F equals ma. 2g is bigger than the r. 2g minus r is equal to mass times acceleration, which is equal to 2 times that value we've just found, 37.5, and then rearrange that to get what r is. So r works out to be 2g plus, what's that, 675 there. So r works out to be equal to 690 newtons if I do it to two significant figures, which I need to do because we've got a g in my question there. Yeah, so that last part's fairly interesting. Parts A and B should be really, really standard and straightforward to you. Hopefully that all makes sense.